Thank you for inviting me back. It's always good to come back to Hopkins, although this room, I think I gave a talk in this room once, but it wasn't here when I was a grad student. So I'm looking around the room to see if there's anybody who was here before I was. Is David still around? Oh, yes. Okay, good. One person. Anyway, this was a field when I was a student, and so it's kind of weird to come back. But anyway, I'm excited to tell you about some work that I've been doing with my students and my collaborators at AI2. And so I'll just go ahead and dive right in. I want to start off by sort of situating this work in a longer line of history in natural language processing. So if you were doing natural language processing, let's say 30 or 40 years ago, then to a large extent you would have found that writing a program to solve a natural language processing task was largely about writing rules and pattern matching. And the tools of the day were, depending on what decade it was, they were, when they got more at the formal end of the field, you were thinking about things like regular expressions. And so regular expressions, we all know them because most of us know them. If you're a computer science person, then this is a commonly used tool in programming. But that was by and large, people were writing regular expressions and other similar rules for dealing with natural language inputs, and that we would today probably say this would be a fairly tedious way to go about writing an NLP system. It probably would be high precision, low recall. It wouldn't work very well. But a couple of things that it came with that were really nice. You could understand what your program was doing. We have a really good grip on what a regular expression means when it matches what it means to match a regular expression. And there are certain kinds of theoretical guarantees. Maybe not as many as we'd like, but we know the formal capacity of finite-state machines. We teach it in undergraduate computer science classes. We have a pretty good understanding of what these kinds of systems can do and can't do, and what they will do and what they won't do. And then I entered the field at a time in the very late 90s when there was sort of a new way of doing things, which was based on probabilistic modeling and statistics from corpora. We thought this was awesome. Largely what was going on at this time, though, could be understood as building models that use the same kinds of features that were widely used in the earlier days in rule-based systems. But now we were putting probabilities on them and weights and learning these things empirically from data. So at this point, I think the emphasis in the field shifted to a different set of applications that were much more amenable to automatic evaluation. And these things really fed on each other. Being able to automatically evaluate and build models from data led to this large surge in empiricism. And this was a good and healthy time, a lot of growth in the field. And then in the past decade, we've seen something new. We've seen sort of a new iteration on this where all that stuff, and I should say before I go on that we gave something up at that time. I think most people would agree that while there were certain guarantees, for example, you knew that when you were estimating a statistical model using maximum likelihood estimation, you knew that if you had enough data, you were going to converge on the right model if you were searching in the right family. So the assumptions were often a little bit too strong for comfort, but we had some guarantees and we had some theoretical understanding of what we were doing. You could kind of interpret the models, although you did so at your own risk. So we'd given something up, but we've continued on that path even further. So I would say now, nowadays, NLP is sort of built out of vectors and tensors, and we build these very large models with lots of nonlinearities. Even at the very bottom level, words are now vectors. We don't really have a strong sense of what's going on inside the models, and in fact, we have almost a cottage industry of papers trying to interpret what's going on inside models. At AI2, we jokingly call it Bertology. Do you have that phrase here? Yeah. So like people are, including us, we're trying to probe and understand what's going on inside. And we almost have to do like new empirical studies as if we were doing social science on our neural networks. So this talk represents a line of work that's trying to maybe not give up some of the great things we're getting with neural NLP, like being able to use large amounts of data. I think it's absolutely exciting that we can use very large, unlabeled, raw corpora to get better NLP performance. That's been a dream for a long time. But we've given up something in terms of interpretability and guarantees. I'd like to move us back and to start thinking about some of these things a little bit. So that's what I'm going to talk about today. I'm going to start by introducing one particular neural network we introduced called SoPa for soft patterns, which is interpretable, and it's very much inspired by regular expression-based, rule-based NLP. And then I'll step back a little bit and introduce rational recurrences, which are a generalization of SoPa, and some surprising findings around rational recurrences. There will be experiments sprinkled all the way through, and I'll talk about more recent work published just at EMNLP last month on using sparse regularization to get more compact rational recurrences, almost with much less work than is traditionally done to make models smaller. And then I'll close with a few sort of high-level thoughts and invite your thoughts. Feel free to interrupt me at any point. This talk will be short if I'm left to my own devices. Okay, so I like being interrupted. I was a Hopkins student, so I'm ready. Okay, so when I talk about patterns, so SoPa stands for soft patterns. Patterns are sort of ubiquitous in the previous stage of NLP. They're I don't know, let's just be very concrete and look at some text. So these are examples, these are snippets from movie review corpus. And the kinds of patterns that I'm thinking about are sort of lexicosyntactic things, like in the first example you see a whole list of things and they're all labeled good, right? So good X, good Y, good Z, and so on. So this good something comma, good something comma, good something comma, that might be a pattern that you would want to pick up on if you were trying to build a sentiment classifier. Another one might be as simple as I have flat misguided comedy. I have sort of two things that are both negative words and they're next to each other. Maybe there's a comma between them. The last one is maybe not a great example of a pattern, right? Because I think it's actually referring to the name of the movie. It's sort of a play on words. This is probably not something where you'd find a good pattern that would generalize well. So we're looking for really cheap surface level things that give us cues. I'm not trying to do, this is not a talk about semantics, right? This is all about surface level, easy stuff that you can find if you look at enough data. And if you were building, you know, okay, so go back, it's the 1980s. Let's imagine you're building an NLP system and you've looked at a lot of these kinds of movie reviews. You want to build patterns. A natural way to encode the sorts of things you're looking at might be to build finite state machines like this one. So here I have sort of two things put together. One is a little sort of forward, almost always forward moving finite state machine that matches almost anything, you know, anything at the front, that's the asterisk. And then I'm going to have a positive word, and then I'm going to have this expression portrait of something. And then I can have anything at the end, and I don't really care what comes later. So this is a very specialized little component looking for portraits. Positive word portrait is kind of the pattern I'm looking for. And in order to do this well, I have to have a good list of positive words. So there also is this sort of lexicon component where I list a bunch of words that are all kind of doing the same work for the purposes of this particular little pattern. So you can imagine sitting down with your friends over lunch and writing down all the positive words in English and build it, and you'd be able to build this kind of machine. Okay, so fast forward a little bit, in the 1990s, we would have done something a little bit more exciting. We would have put weights on these different possible words that could be matched, and so maybe we'd say mesmerizing is a stronger match to the concept we're trying to get here, engrossing a little bit less so, self-assured even less so, but they all have positive weights. And so what's happening with these numbers that I'm associating with each of the words on each of the arcs is that when I match a particular piece of text, I'm multiplying together the weights of the arcs that are involved in that match. And I might be choosing the highest matching weight. I might be summing over all the paths. Either way, it's sort of a similar idea. And what I'm going to get is I'm going to get, you know, a match for a mesmerizing portrait of an engineer is going to have a much higher score than the most fascinating portrait of students, and flat misguided comedy at the bottom is going to get a 0 because it doesn't match that path in the middle. And so this feature would essentially fire strongly when I get this nice strong portrait pattern, and less strongly the weaker the match is, down to 0. So okay, fast forward again. It's 2019. We don't use words in NLP anymore. What do we use instead of words? We use vectors. So that actually turns out to be really convenient, because now instead of thinking about like every word is going to have a number associated with it, I can take a function of the vector and get a number. And words that have similar vectors, usually we take that to mean they have similar meanings, are going to have similar scores. So how do we do that? Well, we associate with each arc a weight and a bias term. And when we want to score a particular word, say X, we look up its vector, we take an affine transformation of that word using the weights and bias, we take a sigmoid, and now our transition weight for that word on this arc is going to be given by this little tiny one-layer neural network. Okay? That's the only thing I'm going to change. Everything else is going to stay the same. I still have a transition function that's associated with arcs. The structure we decided when we designed SOPA was that we would generally be moving forward through the finite state machine. So the states are in a particular order. There's one start state and there's one final state. And the interesting things happen when we move from state to state, from left to right. We added self loops so that the pattern can be a little bit stretchy. You can insert extra words. In some versions, we added epsilon loops, epsilon jumps, so that you can go from state to state without consuming a word. But basically, it's kind of a forward chaining match. And all the parameters are associated with these self loops or forward passing transitions. When I choose the number of states, what I'm choosing is the length of the pattern, the sort of core of the pattern. Yeah, question?
You have different weights for each
Yes.
for each arc.
Yes, each arc has its own parameters. And essentially what that means is each arc is looking for, you can kind of think of the weight vector associated with an arc as, this is the word I would like to match, because you're going to take an inner product with the word vector you're consuming. And then the bias is sort of telling you how big the radius around that word is, right? So if it's a large bias, you're basically open to more things. And if it's a large negative bias, you really want something close to this word before you go through the sigmoid. So if you take all of these, if you sort of ignore the local weight vectors and look at it at this level of abstraction, for every word, what you've got in your parameters kind of stack into a matrix like this that's mostly zeros. It's a very sparse transition matrix because the structure of the pattern is that you're always moving from left to right across, or you're doing self loops. So what's nice here, and again, this is by design, is that the number of parameters you have in each of the transition matrices is linear in the length of the pattern. So you choose the pattern length, and then this is like really all you need, is one sort of word vector for each non-zero entry. Yeah?
Where exactly do you have the epsilon transitions?
The epsilon transitions, great question. I believe, I'd have to check the paper to be sure, but I believe we have one epsilon transition on each, between each pair of consecutive states. So you can skip anything. Yeah. So, okay, so nice property of this model is you choose the pattern length, and then the number of parameters is linear in that and linear in the size of your word embeddings. And then once you've sort of set up a model this way, your match score takes a really nice simple form. So say I take flat misguided comedy and I plug it in. When I plug that into the neural network, what I'm doing is I'm looking up the transition function for each word. That means plug in the word vector, pass it through each of those little squashing functions, get a very sparse matrix that's one diagonal plus an off diagonal, and then I'm taking a big matrix multiplication. We add in maybe a start vector and an end vector to cap things off at each side, and maybe you add a little bit of a multi-layer perceptron or something at the end. But this is essentially a one pattern SOPA neural network. That's all it is. What we actually do in practice is we run multiple patterns, right? You're never going to build a full sentiment classifier with just one pattern. You need more of them. So this is just sort of a visualization of two of them. What's happening is each of the words is passing in parallel to each of the finite state machines. My first pattern has 5 states. My second one has 3 states. And what's happening is the hidden states of the neural network equate to the forward probabilities or the forward scores that you would get if you ran the forward algorithm. Over the words, just like back in old dynamic programming days, if people remember hidden Markov models and the algorithms for finite state machines. So you can actually interpret each element of the hidden state as how strongly am I in each of these states at each time step as I consume the words from left to right. And then we do a little bit of max pooling at the end, which basically says, okay, what's the strongest match from each of the patterns? And essentially after that, I can do a linear transformation to get my final score. Right. So think of this as the forward score vector at time step 1, the forward score vector at time step 2, or the Viterbi score if you use maths.
What if you have a pattern that tries to match both the front sentence and the back
Not sure I understand what you mean. Like it's got two parts and there's a gap in the middle or something?
Say I just want to match, say, adjective nouns, and that occurs many times in the sentence.
Right. So what you'd probably have is high scores in more than one of the bubbles in two different places. Yeah. Depending on which semi-ring you use, you're going to either be like summing up over all those matches or taking a max. Your choice. Yeah. Any more questions? Okay, so I don't know. I was pretty excited, but I'll get to the experiments in a minute. I know that's what really matters, but I was excited by this because I had this sort of annoying feeling ever since recurrent neural nets started popping up in NLP that they looked a lot like things we'd been doing before, right? We talk about the recurrent equations for finite state machines and hidden Markov models and so on. It felt like we were doing something with message passing, although that's not usually the language that gets used when we talk about neural networks. So finding like a way to unify both of those ideas was kind of compelling to me. This doesn't have a full probabilistic semantics. Notice that these aren't really probabilities. We're not doing probabilistic reasoning. We're not doing probabilistic inference. But you can take finite state machines and think of them as pattern matchers, and then everything fits together very nicely. Okay, so here's what we did. We had 200 patterns in our model. We varied the number of states, probably an even split across 2 to 6 states. And so what's happening when you pass text through the neural network is it's going through all 200 patterns in parallel. 200 is maybe too many. I'm not really sure. Later in the talk, I'll come back to this idea that maybe we can do more with less. But 200 felt like maybe enough. Sentiment classification is not that complicated a problem, we hope. We explore. I'm going to give you results on 3 data sets. There's an Amazon product review data set, Stanford sentiment tree bank, and then this rock stories corpus, but we're only using it as a binary classification between right and wrong endings. We're not using it the way it was designed. We're using it more as a style classification task. And then I've got some baselines. There will be a logistic regression model built with a standard hard pattern learner that's not using neural networks at all. There's a CNN, there's a deep averaging network, and then there's a one-layer bi-LSTM. So this paper was published before transformers. I'm not comparing to transformers. The goal here is not to get the highest number you can possibly get. I'm sure our numbers are pretty far behind the state of the art on all these data sets. But at that time, the bi-LSTM was sort of the received model. It's what everybody would have expected would have been the starting point. And it performs at a certain level that we want to compare to. I'm not going to talk a lot about hyperparameters today, but I am going to mention that in every experiment I show you, we did random search for hyperparameters, which is definitely what I recommend. And we have a new paper at EMNLP that I'm just going to briefly plug by Jesse Dodge and some other collaborators discussing the state of hyperparameter reporting in NLP papers, which who here has tried to replicate work in an NLP paper and found that the hyperparameter details were impossible to find anywhere in the paper? Yeah, okay, enough hands are up. So take a look at our paper. We have a nice sort of prescriptive card that says these are the things you should always report when you do hyperparameter tuning. Here are some additional details you ought to look into, like what would happen if I did less hyperparameter tuning is a very useful question for other people who might be replicating your work. And we have some sort of nice suggestions there. So take a look at that. I'm not going to belabor the point today. I can't show you all the things I would like to show you about our hyperparameter searches because we hadn't written that paper yet. Yeah, Ben.
Clarifications, how about the logistic regression part pattern? That's going to be over a set of pre-specified patterns or some giant enumeration?
No, pre-specified patterns that are selected using some methods from 2008, 2010 that were like, yeah. So it's supervised learning, but you get hard patterns out. Okay. So let me explain what we're looking at. So each dot is a data set and a model. The colors are telling you which model. The bubbles around the dots are telling you which data set. X-axis is accuracy, so farther to the right is better. Y-axis is number of parameters on a log scale. People don't talk about this too much, but generally speaking, less parameters is better, right? Smaller models are better.
So the LSTMs are the red dots, and what you see is that they tend to perform really well relative to the most of the competition, but they use a lot of parameters. They're lower down in the plot. SoPa is, in two out of three cases, it's actually doing better than the LSTM with roughly an order of magnitude fewer parameters. It does, in the Amazon case, which is the biggest data case, it's a little bit behind, but not much. And this is using all the data. So I don't know. This is the kind of result that I get really excited by because I care a lot about the small data case. Most people I talk to who are not NLP researchers want to build things like text classifiers, and they don't have a ton of data, and they don't have a huge budget to get a huge amount of labeled data. And so I'm more excited by the rock story and sentiment classification task. When we take Amazon and we reduce the amount of training data by orders of magnitude, SoPa holds up better. So here, x-axis is the amount of training data. As I move to the right, I'm using less, and accuracy is the y-axis. So that purple bar is holding up much better as I move to the right, when I'm using as few as 100 training examples. Yeah. We are using pre-trained word embeddings, but this is still pre-Elmo. So it's like, I think it was glove. Yeah, that's right. So you are using a lot of data for that, but that's raw data. Okay, I didn't talk a lot about epsilon transitions. If I'd known Kevin was going to ask, I would have diagrammed what the model looked like, but you can include them, you can take them out. The paper explores what happens if you have them or don't. They do make things a little more expensive computationally, right? Because you have this extra thing to consider. The addition operations I showed you can be replaced with a max. And if you do that, what's happening is you're essentially running the Viterbi algorithm for weighted finite state machines. Your neural net is a Viterbi algorithm. I think that's like super cool, and it offers you, I'll show you in a minute, some really nice ways to interpret what's going on in the model. Another interesting point for people who like thinking about how models connect to each other, if you take away the self loops, if you take away the epsilon transitions, and you take away the sigmoid, then SoPa is a convolutional neural net. Right? It's not able to look any farther than the width of the pattern, and it can't skip. It's basically just sort of matching at every point and comparing across the matches at every point. It's like a sliding window. So that's kind of cool. There's a connection between convolutional neural networks for text and recurrent neural nets. So that's why we titled the paper Bridging CNNs and RNNs. There's a whole bunch more experiments in the paper I won't go into. I want to instead pitch to you qualitatively that this is a model that gives you nice interpretability properties. So what I've done here is I've taken instances from the data. I think this is the development set. And I found the pattern, where do the patterns match that are associated with a negative sentiment score? And so they kind of make sense, right? It's dumb, it's just not scary, too self-conscious, opaque story. For some reason, hippies is negative. I guess nobody likes movies about hippies. It's always important to think about these things in the context of the task, right? There's nothing wrong with hippies, but when it comes to movies. And then here are patterns that match with a positive score, acclaimed actors and actresses potentially moving, high drama, is inspiring, especially for. Notice they're not always syntactic phrases. In any case, I thought this was really nice. And again, you get this when you use the Viterbi version of the model where you're getting the highest match, right? You can say, where's the highest match for each pattern? You can also take a pattern and say, what are the words, or what are the strongest matches that you saw of this pattern in a data set? And so that portrait of pattern I was talking about earlier, that actually was one that our model discovered. It learned this like positive word portrait pattern by itself. Okay, that extra word at the end, maybe not so important, maybe not so important. Maybe we would have done better if we'd had a smaller pattern here, but this is the way the chips fell. Lists of positive words, honest, enjoyable, soulful, scathing, and joyous. These are, reasonably, they're probably not the things humans would have come up with if you asked humans to sit down and write patterns, but you can see where it's going. You can see what kinds of things it's getting at. Also negative ones. Apparently people who write movie reviews like to use an adverb before a negative word like dull or incompetent. I think phlegmatic is a negative thing when it comes to movies. Does anybody like phlegmatic movies? I'm not sure what a phlegmatic movie is.
Questions at this point? Yeah.
You might have mentioned this previously, that the objective that you're creating is still just sending classification.
That's right. It's the log loss. Yeah.
And so we're just learning the way syntactically that each pattern are.
Yep.
And so you have to decide the number of patterns.
Yep.
How many words each pattern represents.
That's right. The length of each pattern. Yeah. Yeah. And then, you know, all the usual neural net hyperparameter nonsense. Yeah. We didn't think too hard about it. We said we're going to have 200 patterns. They're going to vary in length from 2 to 6. And I think we did an even split across those. Yeah. You guys are doing great, like priming me for the last part of the talk.
So between Kirby and actual forward.
Which worked better?
Yeah, it seems like, I can't think why, but it just seems like Kirby might be bomb horribly, but forward also might be more expensive, like it's still.
Yeah. So this is the part where I tell you I don't remember which one worked better. I don't think, what I do remember is that the difference wasn't that striking. It wasn't like a major finding that it's way better to use one or the other. I think it changed with the data set. There was not a clear enough difference that it stuck in my head. But yeah, I have a similar intuition that I would probably want it, if I cared more about interpretability, I'd probably want the Viterbi one. But if I cared more about accuracy, the summing match would probably work better. The summing one does look more like a traditional RNN. Yeah.
I must have missed how you get a finite pattern length when you have epsilon transitions. You're able to talk fairly specific.
So all that's doing is saying, so suppose I have L plus 1 states. If I use no epsilon transitions, that's going to match L words.
I see. So you're skipping states, not skipping words.
Right. Okay. You're always going to consume all the words.
Okay.
Yeah.
So when you say pattern length, you're actually putting an upper bound on the plugin.
On the part that matches. Now, remember, there was a self loop at the beginning and the end, so you can skip over anything at the bookends. Okay, great. So far, summary. SoPa is a recurrent neural net. It equates to a weighted finite state machine that stores sequences of word vectors. It calculates those scores in parallel across many WFSAs. Works pretty well for classification problems. So what I took away from this is that an RNN, I was really annoyed. I did not like RNNs until we wrote this paper. And now I came away from this feeling like, okay, RNNs are not like my cats, inscrutable and completely disrespectful of theory. If you want to play with the code, there's a download there. I'll move on. This is the part where I'm going to venture towards being slightly theoretical, but I'm not actually going to give you very much theory. So we stepped back from this project and said, this is great. We see this connection between finite state machines and neural networks. How far can we push it? What's sort of the right way to talk about this subclass of recurrent neural networks that we can also view as finite state machines? And you know, is there precedent for this? So we did a lot of reading, and it turned out nobody had quite identified this class. So we gave it a name. We call them rational recurrences. That is not meant, I feel slightly bad about that use of the term rational, because I really hate when people use cognitive words to describe math. So like attention is really annoying. I hate the name attention because you know it's like leading us to think that there's this cognitive mechanism when really it's just a mathematical function. But we're using this word with following the precedent of people talking about rational series and rational kernels. So this is a word that evokes the idea of weighted finite state machines. That's all. We're not telling you that the models have rationality. Okay, good. Not overclaiming. So we're going to say that a recurrent network is rational if its hidden state can be calculated by an array of WFSAs over some semi-ring whose operations take constant time and space. So we don't want to pack a whole lot of extra computation, and we don't want to hide extra work in the semi-ring. We're really trying to limit the class. So we put a name to it, and then we realized that there are many examples of rational recurrences already out there in the literature. They just hadn't been called that before. So one example is the simple recurrent unit, whose functions look like this. So there's an f of x function that gets used twice. So there's some parameter sharing between these two arcs in kind of an interesting way. A single part of the simple recurrent unit only uses two states, but of course,
if you were putting this model to work for a real problem, you'd probably have a whole bunch of these things stacked up on top of each other, working in parallel, just like we did with SOPA. And so we kept reading, and we found this was just one of many examples. It turns out a whole bunch of things can be viewed as rational recurrences. It took a little bit of work to convince ourselves of this, and so if you read the rational recurrences paper, a lot of it is sort of introducing intermediate models and showing how these things that already had been used and introduced are rational because they reduce to this model with this bell or whistle turned off. So if you love that kind of thing, this paper will be a fun read for you. All I'm going to say here is there's a whole bunch of them, and if you can write down a finite state machine, you can build a rational recurrence out of it by definition. This does open up some really interesting questions about sort of what are the families of functions that we can consider when we build neural nets for NLP. And so, rational recurrences define one sort of strict subset, probably strict subset of recurrent neural networks. We are pretty confident that LSTMs and other popular models are not rational, but we didn't have a proof as of the time we wrote this paper. Gail Weiss, a student in Israel, and Will Merrill, who works with me at AI2, are working on some follow-ups here that will clear up a lot of these open questions. But this is still kind of where it officially stands, at least. But the interesting thing to remember is that rational recurrences are basically equivalent to weighted finite state machines, right? They're calculating similar functions, and that is something you should view, I think, as a kind of straitjacket. You're limiting what your model can do. I realize people tend to not want to do that. The current trend in NLP, I think, has been moving towards less and less restriction, broader and broader classes of functions that can hopefully learn almost any pattern. The reason that you want to restrict what your model can do goes back, I would say, to linguistics. You want a theory that's tight, that captures exactly what happens and no more. But it also has there's a very practical reason to want to limit what your model can do and not have infinite capacity to do anything. And that's that your data is still finite. Even in the age of BERT, even when you have massive amounts of data that's labeled, it's still finite, and we have no idea what the sample complexity of any of these models are. So if you know that you've got good assumptions and you can bake them into your model, then you're probably going to be able to do better with less data, which again is the case I think I care about the most. Okay, end lecture. Yeah, please.
You might have taken it, but I think it's very scary. So what makes it not rational if the computation takes more than one?
That you cannot, so essentially what you're getting when you have finite state machines is sort of finite memory, right? There are if you go back to your theory of computation class, there's all kinds of languages you can't represent with a finite state machine, and they usually the kinds of things you can easily prove aren't regular languages, are things that involve like memorizing an unbounded amount of things, or knowing counting, right? For example, how many times have I seen symbol A? Finite state machines can only do that up to a certain point because they have finite states. So the transfer over to neural nets would be how much of the history and how far back into the history do I have to remember? And if I have to keep track of an arbitrary amount of things, then I'm probably not going to be rational. That's the very hand-wavy way of talking about it.
So it's more like you think it's probably not rational versus like there's like some mathematical reason why it behaves like something outside of constant time and space.
The constant time and space thing is really just meant to keep ourselves honest. We didn't want to sneak extra neural net operations into the plus and the times in the semi-ring. This is more about, I think the rational, not rational thing, the interesting part of it is like what from the history do you have to remember? So yeah, I hope that in 6 months I'll have an awesome new paper to point to that gives great concrete examples.
Yeah, I guess that was more of a question, like, do you think that you're going to relax that distinction?
Well, we're not going to change the definition of rational recurrences, but I do think that there are going to be interesting families that sit between the full recurrent functions and rational. Absolutely, yeah. I think there are another way to think about it is rational is one property. There are probably some other properties, and the circles probably overlap, and there are probably interesting intersections. And yeah. What I'd love to see is, a Chomsky hierarchy type representation, but I don't think it's going to be that simple. Yeah.
Can you briefly say how do you go about showing that some network is rational?
The way we did it was we constructed the finite state machine and showed that the recurrent equations were the same. Yeah.
So it sounds like any neural net that has a bounded number of parameters and finite precision would be like infinite. We've always used it, so we can't put limit on how much we can.
I don't think that's right. I mean, the finite precision thing kind of throws me a little bit because usually we don't use that.
Right, yeah.
But
in practice, it seems like if your states you're passing along have some limitations on how much you place, then
yeah, I think you're probably right, but we don't want to lean on that. Yeah, but I think you might be right. Yeah, so I'm imagining like an idealized LSTM that has true, true real numbers. Okay, so going from here, we decided to turn to language modeling, which has become, as you all know, very important in NLP, and we knew that when we were doing this work. So we basically said, okay, before we were thinking about these sort of discriminative classification tasks, let's go back to one of the core problems in NLP and build language models that are using rational recurrences. And because language models traditionally before the rise of neural nets in NLP were Ngram models, we decided to start with the very simplest rational language models we could build. So we designed a Unigram model that looks quite a lot like an SRU or a TRNN or other things in the literature. There's one function for the single transition that's matching the single word, and then another function for what happens after that word. And then we have a Bigram model that has two different functions for the two different steps, and then the natural thing to do is to take the interpolation of the Unigram and the Bigram model by taking a weighted sum. So all the mathematics of combining language models through interpolation transfers here, but it's a recurrent neural net language model that has essentially a finite state view of the world, a finite history. And so we wanted to see how well this would do. And sort of, I guess the reason I think that we should go about trying to find these abstractions, things like rational recurrences, is exactly this: to design models that have properties that we would like to test out in particular. So up till now, I think recurrent neural net language models were typically built because people had some intuitions about what more you wanted, or you wanted to restrict the computation in a particular way. But it was always about the language model, the neural net function. Now it's actually about saying we have states underneath, we have patterns, and we have this finite state worldview. So I'll show language modeling task on Penn Treebank. I'll briefly talk about text classification experiments, but all of this is compared to the Lay et al. LSTM, which was the sort of LSTM done to death, hyperparameters optimized very carefully, strong model. Probably not state of the art now. I imagine transformers are doing better, but at this moment, this was kind of the gorilla. And so we use random search when we're doing hyperparameter tuning on the text classification case. In the other cases, we're using what Lay et al. Found with their extensive search. So they're getting the benefit of a lot of extra work. So here's where we are on language modeling. If you match the number of parameters, any of these three models, this is the blue bars. If you match the number of parameters to the LSTM, this is a 3-layer network. You're doing considerably better. Even with only 2 layers and less than half the parameters, all of these are doing better. The interpolated model gets better perplexity, lower is better, than either the Unigram or the Bigram, which is kind of encouraging. Yeah.
How should I interpret the colors of the arcs in the Unigram Bigram case? Are they sharing parameters, or is it just...
That's a great question. I think the blue ones are not parameterized. I think the blue ones are all ones. The idea is that... Yeah. Right. And then on text classification, this is just averaging across several different data sets. And what we see is that there's again a lift over the LSTM, and the interpolated model is working better. So Surprisingly, you can do pretty well on these problems. You're not, by switching from at least an LSTM to these rational models, you're not giving anything up. That's like really all I wanted to prove here. I'm not sure where the transformer is on this data set. I'm also not sure what would happen if we went for 12 layers on the rational model. Right? It might be doing similar things to the transformer. I think it has fewer parameters. It definitely will have fewer parameters. So what to take away here? Many of the models people have already come up with are in fact rational. The class is practically interesting, or at least was a year ago. Hopefully I've made the case that reducing the capacity or expressive power of your model may have benefits. It's not a bad thing to think about. And then there's one caveat here, which I hope somebody, maybe people in my group will have an answer to soon. All the theory, everything I've said about this relationship between finite state machines and rational models is about one layer. But in fact, in practice, we're often using two or more. And so I'm not sure that when you start using more layers, you get more expressive power. I think you do. I think Gail and Will are going to have some proofs that make this more clear soon. But it's not clear what family we're in when we start adding layers. I had an initial intuition that maybe you have as well, that when you start stacking multiple layers of rational networks, maybe you're composing finite state machines. No, it's wrong. Sorry. Don't waste time on that. Okay, the last thing, how am I on time? We have till 1? Okay, but you guys interrupt me, so it's good. I can keep talking. Okay, so the last bit is fairly short. This is the most recent paper. This is work by Jesse Dodge, who's graduating soon. In the original experiments, I said we have 200 soft patterns, and we vary the number of states. I think it was an even split from 2 to 6 across those 200 machines. What we'd really like is for the model to learn how many patterns it needs and how long they should be. So really what we want is the most compact model we can get, the smallest number of patterns we can get away with to learn to do the task well. And so there's a tool that we had back in the previous iteration of NLP called sparse regularization that would let us do this during learning. We don't have to actually search over architectures. We don't have to treat this as a hyperparameter. We can set this up as part of the learning objective and learn a model that's compact as we go. So I'll briefly review how that works. The starting point is something called the Lasso. Do people know the Lasso? If you're building a linear model, the Lasso is a great tool for pushing a whole bunch of the weights or parameters in your linear model to 0. It's just an L1 penalty on the weights, and it was classically used more than 15 years ago in NLP. It got a lot of mileage in NLP. I'm going to skip over the why it works because people here are somewhat familiar. It's really cool theory behind the Lasso, and it's also one of these things that was discovered many times in many different communities. So I worked with someone who came out of the sort of information theoretic compressive sensing world, and he told me that the Tibshirani paper was like 15 years later than it had been discovered in that world. I think it's been rediscovered many times. So no offense to anybody, it's a great idea. Great ideas are often rediscovered. A fascinating generalization that was discovered a little later is called the group lasso. Do people know the group lasso? A few people, okay. So the idea in the group lasso is that you have some notion of how the parameters group together. And what you're doing when you're learning is you're encouraging whole groups to get zeroed out. And so this is kind of interesting. If you define the groups in certain ways, you can recover the lasso. So if every parameter is in its own group, it's the lasso, right? Not very interesting. If all the parameters are in a single group, then you've got an L2 regularizer called the ridge. You're basically saying, I don't care. Once you use one parameter, use all of them, but I have a preference for all of them to go towards 0. So what it looks like mathematically is that expression on the right. It's a sum of L2 norms of the groups, or an L1 of L2 norms. It's often described as a mixed norm. So this is kind of an interesting idea. We explored it in NLP. I couldn't resist putting one slide of parsing results in this talk. This is from 2011. We were using the group lasso to select features in a linear model for dependency parsing. So this was Arabic dependency parsing, pre-universal dependencies. And what we found was that we could use the group lasso to get better performance with a much, much smaller model by taking out whole templates of features. If people remember writing feature templates, Mark is smiling because he remembers writing feature templates.
Copying other people.
Or borrowing, yes. They were passed down, kind of like the way hyperparameters are passed down from senior grad student to junior grad student.
You couldn't figure out just by reading the paper.
You had to know. You had to have friends who worked on the problem and get their feature templates. Vintage feature templates. Anyway, the question was, could we use this for neural models? And the main thing that blocks us, I think, from directly applying this to neural models is that your standard neural model does not have a notion of a group. There aren't parameters that you would sort of think of together as if I block out this set of parameters, my model gets naturally smaller. Maybe at the layer level with highway connections or something like that, and I think people have explored that a bit in computer vision. Rational recurrences, they're a perfect fit. The very natural way to define your groups is around the states in your finite state machine. So here's what it looks like. That's my model at the bottom. It's a little different from SoPa. It's a little different from the others. I've got self loops. I've got a forward chain. And every state after the first one can be a stop state. So the way I'm going to think about groups is if I associate all the parameters of a particular state as a group, and I zero them all out, that state has become inaccessible. So what I'm doing as I'm zeroing out parameters is I'm chopping off end states that I don't need at the right end of the model. So you train the model with a group lasso, one group per state. You take away all the states whose weights get close to zero after you've converged. And then we do some fine tuning at the end where we go back to the original loss function and fine tune the model just on the new model with less states. So we've chopped out all the states we don't need. Thinking about this experimentally was a little tricky. You have to come up with reasonable baselines. And to do that, we basically did similar things to what we had done before, where you either say all the patterns are unigrams or bigrams or trigrams or fourgrams, or we have an even mix of the four. We did this with Glove. We did it with BERT. You can see the paper for more details. What you're basically hoping for is a picture like this, where as you move to the left, you're getting a smaller model, but you're maintaining high performance. And that's, in fact, what we see across several different data sets. This one's probably the most exciting because it's actually using BERT. It's 2019. We have to use BERT. So now we're using BERT word vectors. And we chopped the model down from the largest were like 48 states, or sorry, 48 transitions, a quarter of that size, and we haven't given up anything on accuracy. We're above 92. And what I love about this model is I can put the whole thing on the slide in some sense. So what I'm showing you here are the four patterns that remained after we did the sparse regularization thing. I'm visualizing each one by showing you the top matches. That CLS thing is a very BERT, that special BERT token. I don't think we're done. Like, I don't think this is the most interpretable thing ever. I'm showing it warts and all. I could put the whole model on the slide, and that's my bragging point. But I don't love it, right? So at the top, you have this like R-perfect / definitely recommend / excellent product / highly recommend kind of finite state machine. The next one is seems to talk a lot about heat and cold. I think this is the kitchen data set. So is heating good or is heating bad? I think heating is good. No, perfect cold. I think negative. I think this is a negative scoring pattern. I don't know what's going on with the last two. Well, the last one is about jamming. Things jamming is generally bad in kitchen reviews. I don't know. I think it's a feat that we can get high performance and put the whole model on the slide. I'd love it if these patterns were something that made sense. Right, so still more to do. The main takeaway in this work is you can use these regularization techniques from the old days. You don't have to do everything through hyperparameter tuning. We don't have to do massive neural architecture search, as Google might have us believe. We have some powerful tools that still work here, and we can make smaller and more compact models, which I think is appealing for many reasons. Any questions before I wrap up? Yeah.
So the structured visualization that you're applying essentially seeks
shorter patterns. And less patterns, because some of the patterns actually get pushed all the way to 0 all the way through, and then they're just gone.
Could you add regularization such that it increases distinctness between the patterns? Like, are they all basically matching the same pattern?
I don't think they are. You might be getting that for free. I'm not really sure. I think that tends to happen. My intuition, although I have no theory for this, is that neural nets tend to do that already. because you're training end-to-end one big model, and so differentiation is always going to have a benefit. But it's probably possible that you could put some kind of entropy in there and encourage diversity. That might be interesting. Yeah.
So you're using L1, L2 mixed norms.
Yep.
There are other kinds of
Mhm.
norms like L1, L2.
Yep. Didn't play with those. This one has the, if I remember correctly, this one fits nicely into the standard SGD setup. It's like pretty straightforward what you have to do to get the regularizer in. Some of the others you have to use tricky algorithms. Like we didn't want to get into proximal grad. Like I got excited. I was like, oh, we're gonna resurrect all this stuff, and Jesse was like, no, we don't need that. We didn't, but there are other options you could explore for sure. Okay, I will wrap up. I think interpretability matters. In other work, in my group and elsewhere, people have been starting to question the interpretability properties of some models. There's, I think, a big debate about whether attention, for example, which is now at the core of a lot of our current models, really is interpretable in the way people tend to think it is. I'm skeptical. I think this really is important because NLP is being used by a lot of people who don't have the same research background we do. They don't understand what the models do. And if we are giving them a false sense of understanding of what's going on in the model, we're potentially doing great harm. I also think for our own benefit, it's useful to know what your models are doing because it's hard to make a model better if you don't understand what it's doing on your data. So I think hand in hand with looking at your data and looking at what your model does to your data, trying to understand what your model does mathematically is important. Again, I'll say it one more time. I think adding constraints to your model families is probably a good thing in most cases in NLP because our data is finite. And you're going to get better generalization if you have better inductive bias. Maybe one day we'll get back to having some guarantees about what our models do. Maybe somebody in here will start developing models we can prove really interesting things about. For now, I think rational recurrences are a step in that direction. And finally, I'm gonna give a plug for a line of work that Jesse and Roy Schwartz at AI2 have been advocating for called Green AI. The energy footprint of AI research, in particular using deep models, is quite large. There've been a number of people pointing that out. This has an added cost beyond the environmental impact, which is that if only 2 or 3 institutions in the world are able to do top performing system experiments and contribute to the state of the art in the field, then that really narrows the set of ideas that are being explored and the ways of thinking and perspectives that are brought into NLP research, and that is definitely a danger. So I'm happy to talk more about that offline. I'm looking forward to meeting with you through the rest of the day. I'll close by thanking my collaborators, the people who gave me money, and take any more questions that you have.
Back to the diversity of patterns now. So the fact that you can maybe half match many things already sacrifices interpretability, because as it's progressing through FSD, you know, once you can do half matches.
What is a half match?
Like, so if you have a pattern that's the weights are give you a high score at the end of one transition.
Yeah.
But it also gives you a high transition
somewhere else.
After another transition and another pattern. So
Yeah.
you're matching multiple things.
Yeah.
I guess FSTs do that.
Yeah.
I guess they do that.
I think it's fine. I mean, I kind of think of an FST like kind of a highlighter. I mean, that's maybe not the optimal way to think about it. Maybe it's a highlighter with a scale of colors and like, you know, some is darker. Maybe it's like a heat map. I don't know. There may be very different kinds of models to think about for interpretability. Maybe this isn't ideal, but yeah.
When you were training the Lasso regularized model, did you have any issues with the memory? So the way I understand it is you have to train the full big thing first, and you only get the benefit of parameter reduction after you've done training.
Right.
So,
I'm pretty sure the answer is no, because those experiments happened very quickly and nobody it didn't come back to me that we were having issues with GPU memory. Usually it's like, hey, Noah, can we buy more GPU? Nobody said that on that project. I think even the largest models in that case were not actually that big. We were not, I mean, obviously we care about making the models small and efficient for those reasons. In this case, it was really more about interpretability. Like, would it be more interpretable? How far could we push it with less transitions? Even the original model was only, I think, 48. So, yeah. I don't think that was an issue, although I do hear about that on other projects a lot. Everybody wants more GPUs, bigger memory. Thank you.